Okay, so we are just starting chapter 13 in Statistical Rethinking, second edition. So we're on the very first question, question 13E1. This question does not require you to use any code, but I am going to use some code to demonstrate some things. And if you want to run this code, make sure you kind of go up to this top chunk here and run everything above. Okay, so oh, and I guess if you're using Colab, make sure that you're in runtime and you change runtime type to R. It defaults to Python. Okay. So let me give a little bit of background here first about what's going on here in this chapter. So this chapter is called Models with Memory, I think, or Modeling with Memory. Models with Memory, I think, yeah. And it introduces several things. And among them is using random effects. Okay, and what a random effect is say that you have some data that can be clustered in a particular way, right? So, for instance, perhaps you take people and you measure their body weight once a year for 10 years, and so each one of these people is going to have 10 measurements. Okay, well, that means then that that the data can be clustered among each person, right? So if you have 100 people, there's 100 clusters in your data set of 10 observations, okay? And so if you're trying to run some kind of regression on body weight, it would be really nice if you had some estimate of each individual's, average body weight, okay? And so what you can do is you can cluster the data according to each person and then get an individual estimate of each person's, average body weight. Okay. So, and so when we do that, because we've taken a random sample of 100 people, we would call this this would be a random effect, right? Because we want to be able to generalize to people that were not in our sample. Okay. And so now each individual person, we can estimate a random effect of each individual person, which is, what is peculiar about each individual person that contributes to the outcome, to body weight. Okay, so I hope that makes some sense. Now, when we do that, we often put all of the random effects, we assign them as being a part of some probability distribution, often a normal distribution. Okay, and what that does, because a normal distribution has more and less probable values, the individual random effects are more likely to be ascribed, the value of the random effect that is more likely to be ascribed are values that are more probable in the prior normal distribution. I hope that makes sense. Okay, so what that ends up doing then is, if you think about the overall footprint of the data, it tends to suck the estimates of the random effect towards some central value, towards some common value, right? So in a normal distribution, it would suck it towards the mean of the normal distribution. Okay, well, actually, I'm going to maybe just demonstrate that really quick. Okay, so let me just kind of demonstrate what I'm trying to get across here. Okay, so let's say that we have a we have a random effect, and we're saying that the values of this random effect assume a normal distribution. Okay, well, you can see then that here 0 is the most common value, right? And so even if we have an average body weight, going back to the body weight example, that is out here, there is it has more prior probability for it being closer to the center, right? So actual values that are farther out on these tails, when they're combined with the prior, that has this peak, are going to be sucked inwards to some amount, okay? And so that's kind of what's happening. Now, what we're asked to decide here is, if we have a random effect, denoted here, okay, which is going to produce more shrinkage, more of this sucking in towards a common value? A normal distribution with a standard deviation of 1 or a normal distribution with a standard deviation of 2? Okay, well, I think that this is fairly intuitive, but the more constrained prior, in other words, the normal 0, 1, right, it's more constrained, it has less standard deviation, will cause more shrinkage, okay? So, so let me just run these two things again. So now I have a standard deviation with standard deviation 1, the tall, peaked one, and standard deviation 2, the lower but more dispersed, okay? And so you can see then that the footprint of the more constrained one, the normal 0, 1, is smaller than the normal 0, 2. And so this is going to result in more sucking towards the middle of these estimates, okay? So, so that's the answer. But let's demonstrate this with the model that was used, or by a modification of the model that was used in the book. And I think that this model was M13.2. And I've modified this a little bit. You don't necessarily need to know how it was modified, but just know that aTANK now has a prior of normal distribution 0, 1 or 0, 2, okay, corresponding to what we're discussing here in this question. Okay, so I've ran both of these models, and now I'm just going to recreate the figure that was demonstrated in the book. I can't remember exactly what figure it is. Let me look it up real quick. It's figure 13.1. Okay, but I'm going to reproduce that figure with the two models here. Okay, so this is code that is basically copied from the book and just rearranged a little bit so that I could apply it to these problems. But let's run this code. Okay, and now here's our two models. So let me just pull this out into another tab so we can get a better look. Okay, so what we're looking at here is all of the blue dots are the actual data. Okay, so I think this is the proportion of tadpoles that survive in different population densities of tanks. Okay, and so each dot represents a tank, or more specifically, the number of tadpole, or the proportion of tadpoles that survive in a particular density of tank. Okay, and so you'll notice that the blue dots are identical in the two figures here, but the black circles are the random effect estimate of the blue dot. Okay, and so you notice that that the black circles are always closer to this mean value here that's been estimated for the it's the average of the random effects. Okay, and so what you'll notice is that in the normal 0, 1, this left-hand plot here, the black circles are farther away from the blue dots. In other words, there's more shrinkage, right? There's more shrinkage towards this mean value here, okay? When you compare it to the normal 0, 2, right? There's less shrinkage here. Well, why? Because the normal 0, 2 had a more permissive prior distribution, a wider footprint of the prior distribution. Okay, so so that's pretty convincing, I think. But just to kind of really beat a dead horse here, I'm also going to plot the cumulative sum of the difference between the blue dots and the black circles here, and then just give a total sum of the total difference between the two models here. Okay, so the black line is the shrinkage in model 1, and the red dotted line is the shrinkage in model 2. And you see obviously that the shrinkage in model 2 is much, much less. And then when we quantify all of that here, the total shrinkage over all data points for model 1 is, these are just, the units don't mean anything right here. There are units, but it doesn't really matter. But you can see that the shrinkage is much greater for the first model compared to the second model. Okay, we'll call that good.